Let's see how to implement the follower object on Python. That will be our uh, problem in this case. It is divided into three scenarios. We have the first scenario where no object is detected, the robot should not move. Then we have another that when the object is detected and we are outside the safety region, we need to reach the object, but do not move inside the safety region. And then what we are going to the third scenario, the final one, is when you are inside a safety region, you already have an object in your pointed, but what happened is that another object enter and is closer to you. What you should do is only just to turn the direction of your robot to point to the new object that is closer than the previous one. We're going to implement it in Python, and let's jump to the code. In the code, well, to have a better use of the time, let's launch our follower control. Here is our launch file. The launch file, we only start an empty world in Gazebo, and also we spawn a two-wheel description, that is the robot with the robotic arm. Let's get back to the object follower Python script. We are importing the map. We have some importing data class to have the typing, a good idea to have it, and also we import from the typing the list, the generic, and something that is called the type bar. That is one that you define as a generic type. We import then some third libraries that are related to the ROS SDK. We import the ROS pipe. Well, I almost forgot at the beginning. We say that the interpreted should be Python. So let's return what I was talking about. We import the ROS pipe. We import the twist and the vector. The twist is the one that has the linear vector and also that have the angular vector. We import our laser scan, that it will be used in our sensor. There is the LiDAR that our robot provides us. In the data class, we have a generic, just to mention that it is that it has an attribute that is data, and it is a generic type, as you can see here. The other one is the laser scan type, that is the blueprint that is provided. But the advantage is that we have it in typing. It matches with the specification when you get the info of that the message type. The name of our node will be robot control node. We put it in a constant so we can change it later. And the safety region that we will be moved, well, that the robot will be limited, is 90 centimeters. That is a circle. And well, yeah, it is almost the same as other programs. We initialize our nodes with the node name. Then what we are going to say is to start our object follower. We are going to instantiate it, and if an error happens, we are going to log as a fatal that our node name has died. And that's all about this part. Let's jump to the constructor. For the constructor part, we mentioned that when the robot shut down or we close it, what we are going to do is to do a cleanup. What does it mean that it is a cleanup? That the linear x will be 0 and the angular zeta will be 0. We publish a 0 to a 0, so our robot will be stopped. And that's all of our cleanup. The reset callback is not necessary. We can remove it. Right here, we can remove it. Well, while I am explaining, let's try to run this program. It is in beginner's tutorial in the package, and the name is object follower. Let's run it. We publish to the command velocity. That is the one that controls the velocity of our robot in the linear and the angular. And then what we are doing is to subscribing to our base scan. That is a topic that provides us the all the info, all the blueprint that I mentioned before. That is the laser scan type. And in this laser scan, the one that is in charge to execute all the action is our recognizer callback. The frequency that will be used in our robot is 2 Hz. It will be executed 2 times per second. Well, that's all. It starts without moving, and every time we do an iteration, we publish the linear velocity and also the angular zero. We only publish those variables because we cannot control other variable in the linear part, neither the angular part, just the x and the z respectively. We have a log info just to mention what is the angular that will be executed, well, that will be provided to our robot. That's all. That's the part that we have here. We can collapse the constructor. Related to the recognizer callback, we have a message that is the laser scan type. As I already mentioned, what we are doing here is filtering all the values in the range because we have a range in the scan type. We are going to filter, and to filter I mean to set it to infinite, all those values that are lower than the range mean and the others that are larger than the range max. In theory, this should be done, but we don't want any misunderstanding. That's the reason that I am filtering those values in our range. Then what we are going to do is to, for example, if I insert a beer, the closest coordinate that will be followed is this one. Well, we are getting the closest, and with that we get the value from the distance from our robot to the object. Then that we get the distance, the value, the magnitude, what we are going to do is to get what is the index that has this value. It gets the first index. So for example, if an object is 1 meter away from the robot and is at index 0, and the other is also 1 meter away but is at index 10, what will be returned is the first one because it has the most priority. And that's all. Maybe it can cause troubles in the future, I don't know, but for this simple approach we can keep it like it is. We don't need to track it. Then that we get the index, we are gonna use the index information to calculate the angle. To calculate the angle is simple because we know that in the opposite direction of our arm we have the negative 180 right here. If we start the beer, let's see, and finish with the 180. It is in degrees, but we need to provide it on radians. And that's all. We only need to take care about what is the increments that we have, so we can do the product of the minimum angle times the increment plus the index times the angle increment plus the angle minimum. So that will give us our value. At the front, it will be 0. Let's put this beer just to start moving. And for example, as we didn't have any robot, any object right here, we put it to 0. That's the reason that the robot was and will not move when it doesn't detect any object. That is the first scenario that is requested. When an object is detected, we don't need to, well, the robot do not need to move. For example, if an object is detected, we need to approach to the object until we reach our safety area. When we reach the safety area, we need to stop, and that's all. The safe region. We say that we are not going to move because we don't desire any movement. And what what the only option that it could happen is that a new object that will be closer, for example in this case, appear. That's the only possible action that can be executed to our robot. For the moment it is only 90 centimeters, that is our safety area, and that's all about our safe region. If we are outside our safe region, the action that will be required is to move our robot. We can move our linear X, and also we can have an angular movement. As you can see here, we have an angular movement, and the robot will start to move slowly. We have a simple algorithm that detects if the robot was moving. If the robot was frozen, as this was the case, and the robot direction do not differ more than 8 degrees, the robot will move. Well, it means that it was frozen and will start moving. And related that we can move the robot, it means that we already was moving. As you can see here, the linear X is greater than 0, but we have more tolerance, that is our radius, that they should be less. The reason that we have this difference is to keep moving our robot, even that the range is not that the difference is greater. And that's all, because if we put it just that the radians will be 8, the robot will start to stop too frequently, and we don't deserve that. The best approach is to try to compensate the angular movement and also to the linear. That there are some areas of improvement that my algorithm do not consider, but that's a factor. Then what our algorithm will do is to get also the angular speed. As you can see here, the maximum angular speed is 0.2 radians per second, and the linear X will be a maximum of 0.2 meters per second. The factor, related to the factor, we have something that I call inverse exponential. The main idea of this is, if the difference in our angles is too large, then it means that the movement that should be applied to our robot in the linear direction will be 0, because we don't want that the robot start moving if the object is at its opposite direction or it's at 90 degrees. Because if we allow this scenario, it will happen that the robot will, instead of approaching, it will be far away from that object. That's the reason. And we already get the angular speed, and we can do it later just to see how we can calculate. And let's insert the other object just to see that it can that it solves the scenario of this third scenario. An object is closer to our robot. This object is closer and we are not moving. And for example, the robot moves from in counterclockwise direction. Let's see that our robot also can move to the clockwise direction, because this object disappeared. The closest one is the other beer that we have. Well, this is our robot working. As you can see, it is working. We can also remove it, just as that we can test the scenario of every object has disappeared. That we already tested, but just to see it again. As you can see, no object is present right there. And to get our angular speed, what we are doing is to get the angle. The angle can be between minus 190 and to 180. Not well, they are not exact value, but approximately. And then we have our speed, so we can have a different speed when the robot is moving and also when the robot is stopped. That it is just to have a compensation later, because right now we know that it can move faster when it is stopped because we don't have any other alteration. And here we have our passive term that will require a compensation, and also if it is greater, it means that we require the compensation to the opposite direction, that is moved to the left. Here we have a direct exponential. The direct exponential will jump in a couple of seconds, but the main idea is that if the difference in your angles is larger, then it means that the robot should move faster. As you can see, it is the opposite of the linear, because we can infer that the angles are too different, than a larger movement in the angular axis, in the zeta axis, can be larger, as we are not going to overpass the object. And if the angle difference is too small, it means that we already approached that object and we don't desire too great a movement, a big movement, because it can cause some oscillations in our robot, and we don't require that. Previously, well, my first approach was to have a linear relation, that it was, for example, if the angle was 0, then I need to move 0. If the angle difference was 180, then I need to move in the factor of 1. And that was all. But the main problem with this approach is that the speed decreases linearly. And for example, for larger difference, then we don't have enough compensation, and it is a kind of bit slow. Here we have our earlier speed, that is our factor, and if we need to rotate to the right, it means that it is the opposite direction, as you can see here, and if we require to rotate to the left, to the earlier speed, and that's all. Now we can jump to the inverse exponential, well, to the direct exponential. The direct exponential is just 1 minus the inverse exponentiation of the delta, and that's all. And for example, and the inverse exponential is 1 minus the direct exponential, and that's all that we have. The publish, we publish, well, we already talked about it. And I guess that's all about my program and the robot. You can see that it is working. Let's play this to right here. It should start moving. As you can see, it starts to move to the closer direction, and then maybe I need to approach that. That if it was stopped, it need to be between the range of difference of 8 degrees, and if it is between that ranges, we can start moving, and that's all. If we are already moving, we can have a tolerance of 25 degrees. That's all. Let's remove this can. It will start moving to this other, but I want just to keep it to and to. Let's see. Does it move? No, because it is inside our safe area. Let's start moving. As you can see right here, it overpassed the 25 degrees, and then we can start moving when we are inside the 8 degrees range. It tells me also increase it to 10 degrees just to wait less time. Well, in this case, we already reached the point. Sometimes it moves faster than I expect. And also, if another object is detected while you are moving, it can take the other direction. And let's start. It will start moving, and for example here it diverges more than 25 degrees, and so it will try to compensate in the other direction that we have. I guess I will return this to 10 because 8 degrees is a kind of slow, but that's all. As you can see, we have some improvements just to compensate. Well, the main areas of improvement, that is the other part, is that have a compensation of the angular and the linear direction, because right now I don't know how to calculate it, but I know that as we are moving in the linear and also in the angular, well, I don't know, I'm inferring that it can be some strange that do not move directly. And also another reason is that, for example, this ball that is at the front, it could also be a reason of failure, and that's all. That's a possible improvement that we need to consider. Another approach that I tried is to have a compensation when it was the first time moved. It was working right in many scenarios, but in some scenarios it was getting without the answer. We didn't reach the object in a reasonable time, so I decided to remove it. That compensation when it was the first acceleration. Right now you can see that it compensates only when it is not moving. Let's wait, and that's all for our robot program. Just wait until our robot reach the can. Oh my god, it's not reaching. Oh, it is reaching the can, but it is decreasing right here is decreasing. Maybe it will be faster if they put a 10. And the other alternative that I use was to remove the first angles, because we know that the first angles do not alter too much the direct exponential, so these movements are greater, and that's all. Because right now it converges to the linear, but it is not fast enough. It seems that it is already within the safe range. We know. No, forget it. Right now we are in the safe. Also, I noticed that, for example, I don't know if these times will happen, but in some, for example, right now we are moving in this direction, like at the bottom to the bottom to the left. Yeah, to the left. But if we move to the top to the left, and also we don't have a degree too large, the road is moved slowly, but I don't know. I do not know the reason. Also, I tried a compensation. The compensation is to multiply our angular speed, that is our factor that we have, only if the robot was moving. That's all that I have in that approach, in that idea. That's all from our robot.